Hi, in the previous section, we've seen the basics of LLMs, what retrieval augmented generation is, and how it can be achieved using AI native vector databases. In these next sections, we'll start with building blocks of these examples. We'll go from examples that you can actually run on your local machine, these models using these smaller models, but yet powerful. And then moving on, we'll just leverage these powerful LLMs to build real world applications. In this example, we'll build a multimodal search engine using OpenAI Clip. Now, Clip, as we all know, is a model that is multimodal, which means that it can take both image and text as input, and the same model works really well on both of them. We'll see what that means if you're not sure in a while. This example is more of a walkthrough, and this is sort of a building block for the next sections as well. So we'll start here and use whatever we've got in this example as boilerplate for the next ones. So let's simply start by installing the requirements. By the way, all this code and other examples like this are provided in the link in the description. You can just go there and follow along. Next, we'll import all the dependencies, and then we'll load this dataset using Hugging Face datasets. This is ImageNet 15 animals, which essentially is a dataset of 15 animals. Because this dataset doesn't contain the labels, we'll just have to build a class for enumerating that. And finally, we'll load the model. So essentially, we'll check if CUDA is available in this environment, which I highly recommend using CUDA if you are on a Colab. But even if you're not, this should be fine as the dataset isn't too large. So we'll load that in memory. So here we are using VIT base 32 model. Creating the embedding function. So I'll quickly introduce embedding in a very quick and dirty fashion. There's a lot more to these embedding and vector spaces. If you're not familiar with them, you should definitely watch or read some more about them, but I'll just give you a quick introduction. So essentially, embeddings are representation of any type of data in higher dimension, or we should say a higher dimension of a trained model, right? So a trained model will represent data or will recognize a relationship between the inputs. So in an embedding space of a learned model, for example, the entities that are closely related will be plotted close by in that particular space, and the ones compared to the ones that are dissimilar, right? So for example, a dog and cat will be much closer because they're related semantically when compared to a dog and a house or a dog and a car, right? So that is the basic idea behind embeddings, which essentially means that we have dealt with embeddings quite a while. In every model that you've trained, for example, some autoencoders or even simplest classification models, anything that is before the final output layer, where you get your final logits, where the model sort of first grows and then sort of is brought down, it shrinks. If you just remove the final aspect of that, what you have is sort of an embedding, right? It is similar to what we are using here. It's not meant for the same use, but essentially if you use any classification model, chop off the final layer, what you're left with is an embedding in a higher dimension when compared to output. Now, here it is quite unique because Clip can represent both text and images in the same vector space because it's a multimodal model. So here we'll see a sample embedding for the first image. The length of it is 512. Now we'll use LanceDB to create a table to save all of these embeddings for the entire dataset so that we can actually run our search engine and power our search engine using that. So there are various ways to create a LanceDB table, and all of them are pretty simple. LanceDB is AI native serverless vector database, which means you can essentially store any type of data here, and it doesn't require any setup. So everything that you store is in your hard drive on your local system. And so you can just scale it up and down in any way that you want. So here we'll start by creating an empty table. Because we've already seen the size or the length of these embeddings, we know what to expect. So we'll just create a schema. Here I'm using PyArrow to create a schema. You can also use Pydantic if you're more familiar with that. So here we know the vector is going to be of size 512, and ID and label are the same. Now we'll just call database.createTable, give it a name, pass in a schema. Schema is optional if you already have a data. So you can either provide a sample data or schema. Here I don't want to provide a sample data because we'll calculate it all together in the next part. So I'll just simply provide it the schema. And the mode is override is obviously optional. I had already created this once and I ran this again, so I wanted to override it. Otherwise it's optional. Now LanceDB accepts all of the Python data formats, right? So essentially you can use PyArrow, you can use pandas data frame, you can use a list of Pydantic tables, or even PyList, which essentially is a Python list of Python dictionaries. So here we'll just create the PyList. We'll loop through the entire dataset. We will get a vector. The vector column essentially is a special column which is used for searching. So this has to be the embeddings, and we can calculate the embeddings by just using the embedding function that we just declared in the previous section. And then we have the ID and labels. It should take a minute or two to build the entire data set for the table for the entire data set. And then in the next section, we essentially do table.add. Because we created an empty data set or empty table, we'll just add this entire data. And then because it's totally integrated with Python data ecosystem, you can simply convert that table to pandas table or to PyArrow, even Pydantic. You should be fine. So here we see the vector for each data set, the ID and label. Okay, we can start doing some stuff now. So let's start with the validation set of this data set, right? So in the validation set of the data set, let's just run this again, make sure that we are still loaded. Okay, so we'll just look at the first test sample. All right, this is a dog. Now what we'll do is we'll just embed this. So essentially to search for this particular image, we just have to embed this using the same embedding function, and then we can search the table to get the closest vectors to it, right? So the first thing is you just embed it and you get the embeddings. Let's just call EMBS. This is the entire thing put together, right? So I'll just show you, break this down, right? This is the embeddings, and here what I'll do is I'll just pass in the embeddings, right? So it says search the table for this particular embeddings, and we want to limit to the first search result. We just want the first one. We don't want all of them. And then we convert that result to data frame. It's just a simple chaining command. So you search for it, you limit it, and then you convert it to the readable format. So what we'll do is we'll just run this and we get something. Let's plot this, right? So let's go to the result.label and print that. So you'll see that I can run this again. So it prints the breed and then the ID. Now let me just plot the ID of this particular image that we just got from the table, and it's a similar dog, right? Now we can run this with another example as well. Let's just run it for, I don't know, 100th image. Then then we have this and we have this, right? Let's see what it is. All right, so it's a coyote. Okay, so what I'll do is I'll just embed this image, which is 100th image, not 1000th. Then we'll plot it. So the most similar one to coyote is a hyena. All right, this works pretty well. We have a search engine that can essentially search through images. Now let's create a function, a helper function that can essentially search by IDs and return top 5 of the matches. So essentially we'll take an ID, we'll go to that particular test column, print its labels, display that image, and then search the table for top 5 of those similar images to the input, and then print them all out, right? So let's do that. This is our the result for the first one. But we've already seen that, so let's do something else. Let's look at the I don't know what's the length, 3000 maybe, if that is that already. Okay, yeah, it's out of bounds. Okay, never mind. We can just do 1200. Okay, right. So it's a tiger underscore cat family, I guess, and then it is now plotting all the other images. So we've seen the RAM usage is pretty high now. So, all right, let's see. So these are all the similar images, and you can see it has essentially found the most relevant ones. As you can see, you don't have to see the labels even to recognize that these are similar ones, right? That's our search engine for images. Okay, now we want to build a multimodal search engine. So let's also look at text, right? This is good for searching via the images. Now let's do the same thing with text. There's the same embedding function, which is embed text. It just tokenizes it essentially. Tokenization is essentially you take the text and convert it in as numbers, as tokens that are machine understandable, because machines only understand numbers, not text. So you're essentially representing language as text. Again, a very dirty definition of it. A lot of things like positional encodings and stuff like that are still at play here. So you should definitely check out the text on embeddings or some videos on tokenizations and stuff. So yeah, we'll just use the same function. Now instead of searching with the images, we'll search with the text, and you can see you get the same dimension output, which essentially is what I was talking about in the first section of the video, which is clip embeddings are multimodal. Whether you search through text or through image, it throws the entire thing, it represents the entire thing in the same embedding space, right? That's the real power. So once we have this, let us now search the table through text. So now let's say I want to look at black and white dog. So what's most similar to it? Right? Can we do that? So obviously we can do that because we have the same vector space. Now let's plot this. So we said black and white dog. So this is probably the closest to that. So you see some white here, you see some black here, and you see a dog, or like something similar to the dog, the same sort of family. Then I mean we can probably do something else as well. We can just say I don't know, like what are the classes that we can play around with? I guess I know, yeah, French bulldog maybe. I'm not seeing that example being used here. So let's just try with a French bulldog, and then let's try to plot that. So we get the embeddings, and yeah, I mean, pretty good for text to image. All right, again, we'll just use the same sort of pattern where we just have a text, search through it, limit it to the top 5 search results, and then plot all of them, right? So we just search for a full white dog, and it should first of all display, or it should display the 5 closest result to that particular text query, right? So here we get a white wolf, which again is close to wolf and dog. For image, for machine, it's very close. They're very similar, right? So it's obviously white, and so that feature is also sort of considered. And the next one we've already seen, and we'll see some similar ones. Again, this is not perfect because you see a white dog might not, the model might, and it's a good example to sort of clear this up. So model doesn't understand what's a white dog, right? It's just representing a particular image in the same embedding space, it sees the image as a whole and not a particular part of it. So it never knows what a white dog is. It just knows some features in the image. So in the above examples, the dog itself contained the characteristic of being white, right? And here as well, like you see, most of the white parts are not on the dog itself, although some are, but its surroundings. Here, again, the model got lucky because the dog itself is white. And it's really powerful. But here you see a white dog. Here the model sees, okay, the white background, which is, okay, some white characteristic. So that's good. And then a dog, right? So it also gives you that result, right? So that's what's happening here. Here again, the model gets lucky. And this is something that you should know. That model doesn't know exactly what you're talking about. All right, so here's some insights that you can get from a simple multimodal search engine built using Clip and LansDB as a vector database to search through the embedding space and find the most relevant examples. We'll build on top of this. By the way, this is really powerful, right? It's until like 2 years ago, this was not really possible, right? And I guess even like 1.5 years ago or 1 year ago, this model was not open sourced. So, you had to use an API to sort of talk with OpenAI API and then get these results. So now we can run these locally. They are much more powerful models than even this, which is by OpenClip. But we'll start here. We'll use OpenAI's stuff, and then the next sections we'll cover more. So this is the first example, and next section we'll cover some more fun stuff.